Let's look at some optimization questions. I really want to kind of show that they all end up being the same thing. Let's look at a classic one that has us, they give us a curve. All right, that's just a nice, easy parabola. Try to draw it decent. And it wants us to fit in the biggest rectangle possible. So, I don't know, I just drew some hypothetical rectangle. We're like, okay, how do we arrange it so we get the biggest rectangle possible inside of this particular curve? Okay, so what do we want to do? We want to maximize area. So let's establish that that's the goal, right? We want to find the maximum area. The maximum area, well, if you want to find the maximum area, the first thing you have to do is write an area equation. So the area in general is some length times some width. All right, let's discuss this. If you look at the picture, see this point right here? That point's on the curve. That point is a certain x away, and it's at a certain height. But the height is 12 minus x squared. Okay, but that kind of tells us everything. The width, that's x. So this distance is 2x. So the area is 2x times this height. But this height is just the y value, which is the curve. 12 minus x squared. And already we're good. We have the area as a function of x. And here's the principle on all of these things. If we get some area as a function of one variable, we can graph it. This would be some negative cubic function. So it's going to look, I don't know, something like that. And what we're interested in the domain of the problem, we're interested in this max. What x value, and then what area does that produce? And it is some maximum. There's a perfect x, an optimal x value that gives us the biggest area. Well, how do you find that using calculus? Well, calculus says that maxes and mins typically are going to correspond to where there's horizontal tangents. Right? We know that the tangent line there has a slope of 0. So if you found the derivative of a with respect to x and set it equal to 0, you could figure out that x value. Now remember, you can do this problem without calculus. We have the area as a function of x. You can just graph this on your calculator and have your calculator find that maximum. It's going to be the same thing. Let's go ahead and show the calculus though. So remember, how do we find maxes and mins? We figure out where derivatives are 0, and then we got to make sure that they're actually maxes and mins. Again, just because you're a critical point doesn't guarantee you're an extreme value. I'm going to go ahead and multiply this out first before I do any calculus and get 24x minus 2x cubed. Now I'm going to take a derivative, so dA dx, the derivative with respect to x, and the derivative of 24x is just 24, and then minus 6x squared. I'm going to set dA dx equaling to 0, which is to say that 24 equals 6x squared, divide by 6 to give me 4 equals x squared, and I can get x equals plus or minus 2, but 2 is the only interesting value because negative doesn't make any sense in this. There's your perfect x value based on that particular quadratic. If x is 2, we can come here and find out what the area is going to be. So then the area, the maximum area, should be 2 times 2 times 12 minus 2 squared. Again, I'm just plugging in x into here. So that's what? 12 minus 4 is 8. 8 times 4 is 32. So let's give all these units. So this would be like 2 meters, and this would be 32 square meters. That is the best way to arrange to get the maximum area. And all of these questions are the same. You're going to get the area as some function of x, and then you're looking for where derivative is equaling to 0. All right, let's do another easy one. Let's say we have some river here. Okay, this is all water, and we want the best fence possible. Okay, the best fence would correspond to you building some fence that encloses the most area. Again, best fence is maximizing the area based on an amount of perimeter. And so, let's just say that they give you have 80 feet of fence. So you know that the perimeter of this thing can be 80 feet, and you want to figure out what's the best area you can do. And again, they do have to tell you it's a rectangle, and in this case, let's say we don't have to bound it here because there's a river, right? Or whatever we're enclosing here, can't swim across that river. Okay, so what do we want to do? We want to maximize area. All right, if you want to maximize area, you got to write the area equation. The area equation is the same thing, length times width. Let's go ahead and call this x and this y, and so then our area is just x times y. And then let's go back to this restriction. Okay, this restriction is similar to this restriction. This told us the height of our box. This restriction is going to tell us that the perimeter of this thing, y plus x plus y, so 80 equals 2y plus x. That's our restriction. It allows us to relate x and y, and then we can get rid of whichever one we want. It doesn't matter what you want to get rid of. Let's go ahead and get rid of x this time. This tells us that x equals 80 minus 2y, and then we can substitute in. So we get area equals 80 minus 2y times y, and so we have the area as a function of y. We could even draw that graph. There's area, and there's y, and this is just an upside down parabola that's got an intercept of 0 and an intercept of 40. And it looks like that. Again, we're looking for the maximum A. We're looking for calculus-wise a horizontal tangent. I'm going to multiply that y in, right? Algebra before calculus. 80y minus 2y squared. And then I'm going to do dA dy. I'm going to take the derivative of A with respect to y and get 80 minus 4y. I'm going to set that equal to 0. And I'm going to solve, and I get y equals to 20. But if y equals to 20, I can plug it in here and figure out that x is 40. And I have the best dimensions, and if you actually wanted to find the area, then you could figure out that it's 800. 800, and let's say it's square feet. Okay, so let's look at minimizing something this time. So let's start out with just a cylinder. And this can be like a pop can. And we want to make the most efficient pop can. And so let's say we've decided that our consumers want 10 cubic inches for the volume. And the question is, we want to minimize cost. And cost and surface area are going to be related, right? The cost is probably the amount of material, and the amount of material is directly related to the surface area. So we're going to be given the volume we want, and then we want to minimize surface area. Surface area for a can that's got a top and the bottom would be 2 circles for the top and the bottom, plus the wall, which is 2 pi r h, right? This is the top and the bottom, and this is the wall. Okay, if our volume needs to be 10 cubic inches, that means that 10 has to equal pi r squared h. I can solve this for h. So h equals 10 over pi r squared, and then I can substitute that into the surface area equation. So the surface area is 2 pi r squared plus 2 pi r h, where h is 10 over pi r squared. Now I'm going to simplify that in a second. 2 pi r squared, the pi's cancel, 2 times 10 is 20, and that's r over r squared, so that's r. And what I've done here is I've found the surface area as a function of r. And again, if you want to minimize surface area, you want to find ds dr and set it equal to 0. That's going to find the horizontal tangent, which will correspond to the minimum. So I'm going to take a derivative. ds dr equals 4 pi r minus 20 over r squared. Right? I just did power rule. Bring the power down, decrease the power by 1. Bring the power down. The power here is a -1, which made it a negative, decreasing the power from -1 to -2. Now I'm going to set this equal to 0. Again, 4 pi r equals 20 over r squared. Remember, if ds dr is equal to 0, that means this is equal to 0. That means that these two have to be equal to each other, right? Something minus something equals to 0. I'm just setting them equal to each other. And then I'm going to solve this. So this is 4 pi r cubed equals 20 divided by 4 divided by pi. And all of a sudden you get r equals 5 over pi cube root. Okay, that is really close. Again, this is an irrational number to 1.1675 or so. And I know I'm going beyond significant digits of what I can measure, but I just kind of wanted to make it a nice round number. And that would be in inches. And then if you find the corresponding height by plugging that back in here, you get a height that's 2.335. This is the best possible cylinder based on that given volume that minimizes surface area. And you will notice there is a relationship here that the height is twice the radius, meaning if you really were going to draw the best can, the diameter, twice the radius, would equal the height. And so it would be kind of a square looking can would be the best possible can you can make. Okay, and let's do one more. We'll do one more minimized problem. And again, we did 2 maxes and let's do 2 mins. So this one's a little story involved here. So this is you, okay, and you are on the bank of a river and you want to get down here. So this is you, and this is where you want to end up. That's your goal. And there's all sorts of quantities I have to give you here. Okay, but your goal is to get there the fastest way possible. So this is the river. This is land over here. And I don't think it makes a lot of sense to stay in the river the whole time because you're not going to be able to swim very fast. And it doesn't make a lot of sense to go straight to the land and down. So I'm going to draw some path that you might take. You might angle back somewhat to the land and then run the rest of the way. Okay, so here are some of these distances. Let's say that the river is 200 meters wide. You are 500 meters north of your goal. Let's say you can swim. Oh, you're a fast swimmer. Let's make it 3 meters per second. And you can run on land at 5 meters per second. And the question is, how do you get there the fastest? And again, the fastest is all about minimizing time. You want to minimize the time. And so let's just kind of go through some of these procedures here. So to minimize time, we need to get an equation for time. But time is just going to be T1 plus T2, right? The time you spent on the water and the time you spend on land. Okay. So how do we figure out how much time we spend on water? Well, we have to go old school here. Remind ourselves of a 3rd or 4th grade formula. The distance you travel is a rate times the time. So the time is the distance divided by a rate. Okay, so we got to figure out this water distance and this land distance. And this is where we introduced a variable. This doesn't really matter. You can make x, make this x. You can make this x. For whatever reason, I'm going to pick this distance to be x, which means the land distance is going to be 500 minus x, right? If this is x, this is 500 minus x. So go ahead and know that. But if this is x and this is 200, then this water distance is just the Pythagorean theorem. Okay, so this T1 is the water time. The water time is the water distance, 200 squared plus x squared, divided by the water speed, which was 3. And then the land time is the land distance, this distance, 500 minus x over the land speed, which was 5. Okay, and look, I have time as a function of x. Just like over here, I had surface area as a function of r. And in previous examples, I think we had area as a function of x in both the max cases. Okay, so what do we do here to find minimum time? We look at the derivative of time with respect to x. We have to take a derivative. dt dx. This might look a little messy, but it ends up being okay. This is just power rule. I'm going to bring down the power, so a half, and then I'm going to multiply by the chain rule. And so when you do that, I need to save a little space. The chain rule gives you the 2x. The power rule gives you the 2. Decrease the power by 1, which makes the square root into the denominator. And then that 3 is just chilling out. And then the derivative over here, well, 500 over 5 is just a constant, so that derivative goes away. And then the derivative of negative x over 5 Well, that's just negative 1/5. It's like the derivative of 10x is just 10. The derivative of negative 1/5 x is just negative 1/5. And again, I'm going to set dt dx equal to 0. Remember, on a graph, this is what this would look like on a graph. If you graph this, time versus x, it would look something like this, and then it's going to do that. Okay. This is the time corresponding to an x value of 0, meaning if you went straight across, and then there's some optimal x value, some best way to do it so you get that minimum time. And that's what we're going to do here. We're going to set this equal to 0, which is again setting these two equal to each other. Those 2's cancel, so let's get rid of that. So that's x over 3 radical 200 squared plus x squared equals 1/5. So I'm just going to cross multiply. I'm just solving this. I'm just getting rid of the fraction. So I'm going to get 5x equals 3 times 200 squared plus x squared. Now I'm going to square everything. 25x squared equals 9 times the quantity. That's just 40,000. Let's just go ahead and write that out. Plus x squared. And I'm going to distribute this. 25x squared equals, that's a 9x squared, and then that's 360,000. Let's subtract the 9. We get 16x squared equals 36,000. Divide by 16, and that's 22,500. And then take a square root, and you get x equals 150. And I guess that would be 150 meters, right? That x value minimizes time. It's the best way if you were here, given all of these values, swimming, running, the land distance, meaning how vertically you are, and then horizontally you are away from your goal. That's exactly how you should aim. So if you wanted to find the angle, you could. If you wanted to actually find the time, you could take the x value and plug it back into here to actually find the minimum time. Anything you can do. At this point, you pretty much have it solved. But again, it doesn't matter whether you're minimizing or maximizing. The idea here is that if you have a graph that looks like this, and you want to optimize, in this case it'd be a maximum problem, you're going to find a maximum by looking for when the derivative is equal to 0. In this case, we found where the derivative is equal to 0, and it corresponded to a minimum value, right? We looked at dt dx. Okay? Hopefully these 4 examples, again, 2 maxes and 2 minimums, were a good review of kind of how optimization works. But again, I think it's a really nice topic because this applies in the real world a lot when you think about, okay, how do you actually construct something to be the most efficient with either time or resources or cost. So this is kind of a pre-engineering type topic.